All right, everybody, it's the last day of class. This video is going to go viral, I just know it. One of them's got to, right? Okay, so we are about halfway through chapter 10, and I was just talking with Shauna here, and she says this is also one of her favorite chapters because I think it really shows a vision of hope for the future. We're talking about integration, and I think before I get too excited about chapter 10, I wanted to share one idea that I read when I read Jared Diamond's book Collapse. So Diamond, I think it was 2008. It was just, well, I don't know how many books he's had. He won the Pulitzer for Guns, Germs, and Steel, which I haven't read, but I did read his Third Chimpanzee, which I highly recommend. Very interesting insights into our own ancestry and relationship to other primates on the planet. But in Collapse, what Diamond did was to compare several civilizations that either sort of did the right thing and didn't consume themselves, or did the wrong thing and are no longer with us. And one of the civilizations that did collapse was Easter Island. They overpopulated, ate all the birds, cut down all the trees, and then started eating each other in relatively short order. And so the issue, and I'm not saying we should not integrate and we should not globalize, but one thing that Diamond mentioned, and let me just so here's Diamond. There's another faculty member here in town, Chris Filardi, who has co-authored books with Diamond. I've emailed him a couple times. I think there's probably some famous photos out here. There's a few of him with the Easter Island in the background. Looks like he was kind of into the selfies there for a little bit. I don't know. He's spent a lot of time in Montana. He's spent some time down at Hull's Dairy, but really a leading thinker in sustainability. Anyway, I'm not going to find the figure I was looking for here, but he did mention that just it looks like just prior to Easter Island's collapse, they were doing a lot of trading among themselves. And so I'm not going to say that like trading itself is a bad thing, but if you end up with local scarcity, you're sort of forced to trade. Like say I'm over here with my cattle, you're over there with your mineral resources, someone else is over here with their water, and we each need some of those to live or to survive. And so what ends up happening is you end up in a trading scenario, money gets involved, et cetera, and some sort of sustainability practices have to be put in place, or eventually there's not enough to go around and the whole system breaks down. So I think it's really important that we understand what the global resources are. That's why the Shramsky paper is so important. I think it's also extremely important that we know what the what these renewable energy technologies we've been talking about are actually capable of, so we don't have some false sense of security, but also that we understand that, yeah, I mean, we like it or not, we are all connected and need to come up with appropriate trading schemes so that planet Earth doesn't turn into a big Easter Island. There's already a lot of refugee problems, as we know. So some of those issues have started, but the more aware we are of them, the better off we'll be. Okay, this was the last little figure in section 10.7, And what the authors have been talking about up to this point is integration. The previous figure on page 488, figure 1016, was looking at how weather patterns will likely drive a lot of the control systems for renewable energy technologies going forward. This is just one example. So if you are a tidal firm, the tides are sort of doing this sinusoidal behavior as a function of the lunar cycle. And you can see that the different turbines, one running on the intake, one running on the outtake, it kind of becomes a two-phase system. You add those two phases together, and you end up with a better looking system overall. So on this one turbine, the water's coming in, and you're making electricity. Here it's going out, and you're not. Oh, I'm sorry. No, here it's coming in. Here it's going out. This is the total at the middle here. It's doing nothing, and therefore this guy isn't making any electricity. But if the other turbine is 90 degrees out of phase, then you add those two together, and you've got a much more stable electricity generation profile. Okay. Okay, so that wraps it up for 10.7. Now, we're looking at 10.8, and this is called some partial solutions. And I'm just going to read through the bullet points. So, future large-scale reductions in greenhouse gas emissions will require a number of tasks to be carried out that overlap in many ways. Decarbonization of electricity. So that means getting off the coal, gas, and oil, and some CCUS. Development of alternative transport fuels to replace fossil fuels. So I'm thinking biomass there. I'm thinking hydrogen. I'm thinking even just Elon Musk's Hyperloop solar train. Let's just go there and fuel the thing off electrons. The reduction of heat demand in the building stock. So just coupling our buildings with the earth. I've heard recently that you are not allowed to build a new building in Germany unless you do geothermal. It's part of the national code. You've got to do it. Development of replacements for oil and natural gas as heating fuels. Right there I'm thinking hydrogen again. Okay, at present there are three main contenders for future energy, and particularly the electricity supplies involving low greenhouse gas emissions. So coal and natural gas fueled system using CCUS. I was on the phone or the Skype with Dane's representative not too long ago, hoping to do exactly that here in Montana with all the beetle kill that we have. Nuclear power, not everyone's favorite, and again, it's a finite supply, and we've got the storage issue, and then finally renewable energy, of which there are many. Okay. A few other things down here. I'm just going to read the last four bullets on the page. So development of demand management and electricity grids. So again, this is just letting the grids become more connected. If it's sunny in Missoula and cloudy in Hamilton, you pipe the electrons down there and vice versa. Strengthening an extension of electricity grids, both to provide short-term time diversity of supply to tap into a wider range of supplies over the year. That will happen. Be much better to go out and get some of this beetle kill now and use it as heat and fuel in the winter, for example. Development of complementary rather than competitive electricity generation. I think showing the tidal system, biomass, et cetera, is a way to do that. Development of hydrogen as a possible transport fuel and replacement for natural gas, so that would be fantastic as well. Okay, electricity demand management. does say that the smart grid involves a parallel flow of both electricity and price information that would allow increased flexibility. So one example, the smart grid, what you might do is put your laundry in your washing machine at the beginning of the day. And, oh, I just got a fantastic idea. And maybe it exists already, but what I think a fantastic thing would just be to have one machine that washes and dries your clothes. Because it's a hassle to take the things out. So you stick the stuff in at the beginning of the day, and you tell your washing machine to wash your clothes when electricity is cheapest, or even free. You know, like the sun comes on your roof, boom, and then your clothes get washed. In fact, there was a neat little segment on NPR last night, I think it was. There's the house in, oh gosh, anyway, I'm going to blank on the name, but wherever Led Zeppelin recorded Stairway to Heaven, it's an off-grid house, and so they say whenever they've got a whole heck of a lot of extra electricity, they just crank the Led Zeppelin. And the neighbors love it.
I did see a brief little part of that.
Oh, really? Yeah, I love it. I love it. I love it. Partying. Okay, so demand management we just mentioned. The next one is grid strengthening and enlargement. So, since the wind doesn't always blow, since the sun doesn't always shine, the grid should get larger, with more renewable technologies. And here's one. So the grid is now out in this lane, the shipping lane, as we can see, and the strengthening part means that the cables are built to last. And right here, I'm just going to read this little bit about finances. It says, typically, an overhead 400 kV AC line capable of carrying 3 gigawatts costs 1.3 million pounds per kilometer to construct. It says placing sections of the cable underground is better from a visual standpoint, but it's $10 million per kilometer. Yeah, so there are some price challenges to making things more robust. So putting it underground, you're less likely to have a failure during a windstorm, for example, but the costs, the short-term costs go up, hopefully the long-term costs go down. Okay, so here's enlarging the grid, possible future offshore international links, currently operating are in red, under construction in yellow, under study are in green, under study and recommendation are in sort of that blue, and then dark blue. Yeah, it's kind of hard to tell the difference. Yeah, I think the gray one is this is the recommended for 2020. And then these bigger orange ones recommended for 2030, yeah. Who knows what's recommended for 3030? We'll have laser beams shooting from the moon or something. Okay.
That would be crazy.
Mid-sea supernodes, and then offshore wind farm development areas. And those are offshore. Those are miles offshore, these blue guys. So. Yeah, so is geoengineering happening? Yeah, it's right there. When you have an engineering project that is, the size of continents, absolutely, no doubt. Okay, using grids to smooth out variability. We mentioned tides already, weather systems. Even down here, there's this thing called desert tech. And even, I'm on page 485, an even more ambitious proposal for electricity grid enlargement is that by the Desert Tech Industrial Initiative, a consortium of large and mainly German companies, which envisions strong high voltage DC, so not high voltage AC, but high voltage DC electricity grid lines between Europe and the Middle East. MENA, Middle East and North Africa countries, figure 1020. Let's take a look at that. So there's your CSP, there's your PV, there's your wind, there's your hydro, biomass, geothermal. So they're hitting the big ones. Brown squares at the bottom left indicate the areas of desert that would be required to supply the world's and the EU's energy. That's no, that's too small. Let me see. The brown squares at the bottom left indicate the areas of desert that would be required to supply the world's and the EU's 2015 electricity demand using concentrating solar power electricity. That seems a little small to me. When I did the numbers not too long ago, you basically needed Texas. And the area that we're looking at there is a little bit, it's a lot smaller than Texas. Let me see. Let me read it one more time. Oh, it's the electricity demand only. I looked at it for all energy demand. So if you took all of our energies and converted them to electricity, and electricity might be, it still seems small. It still seems pretty small. But it's not surprising the size of the solar array would in fact be visible from space. And the dashed lines, there's nothing in the legend saying what the dashed lines are. I don't know if some of these reds are currently existing and the dashed are proposed, but we're even heading out to Iceland where we've got wind, we've got hydro, and we've got geothermal. Not so much on the concentrating solar. You can see that's more in the lower latitudes. Okay, complementary electricity generation, pump storage. That's a big one. We're currently underway for one in Montana at Gordon Butte. It says, although it is relatively efficient at storing electricity, 80% requires large, high-level reservoirs and large volumes of water. Scotland is one place. Heat storage, this is one that I've been on a kick for a while. It's just storing heat. Like right now, I could be storing cold. In the summer, I store heat, and I can just pull the heat from underground when I need it in the winter. What's the question?
No, I'm following.
Yeah. It's different though. With pump storage and water, you're going to lose a little bit to evaporation, but with heat storage, you're just always losing it to convection. Well, you're losing it to everything, but you're losing it to a lot just to conduction.
So you have a basement full of really hot air.
Basement, I would use hot water or even another fluid. Some salt waters have higher thermal coefficients than water. But yes, just something down there that just stores heat. When we did the, and it is of course clear. It says low temperature heat energy cannot be converted efficiently anyway back into electricity because of Carnot's law, which we know. It says, however, the energy can potentially be put to good use, and the required volume of storage is modest compared to pump storage. I did the math in 101 a year or two ago, and if you were to take your neighbor's house, for example, and just convert it into a hot water tank and it didn't have any leakage, if you filled the whole house with hot water and took it right up to boiling, that's enough thermal energy to get you through the winter in Montana. So, like how big does the tank need to be? Well, it needs to be about as big as your house to go completely off the natural gas heating grid. Okay, production of hydrogen and synthetic natural gas, electrolysis. We do have a 100 kilowatt electrolyzer here. It'd be good to fire that guy up again. So what you're doing is you're using electricity, which would be generated from sun or wind, to electrolyze H2O, and then the hydrogen can either be burned or it can be sent through a fuel cell. And there are also some fossil fuel-based hydrogens. I guess I'm not as big a fan of these, but here's the reaction. So if we've got two H2O molecules coming in, and you've got your methane, CH4, what then comes off is your CO2 plus your H2. Now, this could go to the greenhouse. It could go to cartridges. It could go to the beverage industry, etc. Bicycle tires you can fill with CO2. And then this becomes electricity or heat, your hydrogen. So you've just taken regular water, combined it with methane, which is plentiful. The methane could be coming off a landfill, could be coming from dairy farm. Ooh, I like that one. Yeah. And let's read a little bit about CO2. CO2 can also go into sequestration. And did we talk a little bit about the African Lake Nyos in here? Yeah. Here's one issue with sequestration if not done properly. So that there are CO2 pockets underground. I do want to. I think that's what it is. Sounds tasty. So Lake Nyos has a underground CO2 reservoir, which is making it acidic, making carbonic acid. But the bad news, and I just read about this recently, is this 1986 disaster when it erupted. They don't show the pictures, but they do show some dead livestock. 62-mile-an-hour gas plume coming up, spilled over the lip, suffocated 1,700 people. They were just kind of, living there near their nice little lake. But so that's why, I'm a little skeptical when I'm reading here. So CO2 produced does not necessarily have to be emitted to the atmosphere. It can be captured, compressed, and piped for long-term storage.
So that happened.
Yeah. Now, how long are we talking here? Long.
This is hundreds of thousands.
So first of all, nothing lasts forever. Your long-term is long-term. It's not infinite term. Stored in saline aquifers deep underground, large-scale CO2 disposal or sequestration has been carried out for over a decade by the Norwegian company Statoil in its Sleipner natural gas field. In this case, the CO2 is an unwanted contaminant of the natural gas. So it's more generally the separation of CO2 produced by electricity generation or industrial processes, and its subsequent sequestration is known as carbon capture and sequestration. All right. Well, let's look forward to hydrogen now. Let's see how we're doing on time. Yeah, let's just do a couple more slides here. So looking forward to a hydrogen economy, which our former Dean Paul Williamson was a proponent of. He's now off on his own, I think somewhere in Colorado. But the basic chemistry is that the hydrogen comes in, there's an electrolyte, and a hydrogen atom, if you recall, is extraordinarly simple. It's just a proton and an electron. So if it is at the anode, the charge is such that hydrogen will pass through the electrolyte, recombine with air that's coming in. Air has oxygen, and then recombine just to form H2O, and that's your exhaust. And then the electrons, which have come off of those hydrogen ions, then go through your electrical circuit, and you run your toaster, run your hairdryer, etc., and the only pollutant is water. So there's a lot of, I know there's going to be a lot more money getting dumped into fuel cells here shortly. Okay, now here's some, here's a vision for what appears to be a carbon-free grid. So you've got hydro and wind making electricity. This runs the electrolyzer. And again, we've got a really nice one here. It'd be great to have it back up and functioning. The hydrogen is then compressed. And I want to look up these temperatures, because I can never remember what hydrogen's condensate or boiling temperature is.
12.
Water, but we need hydrogen.
Oh, hydrogen's different, yes.
Yeah, hydrogen boiling temp.
400, negative 400.
Yeah, what is that in, 20 Kelvin. Yeah, 20 Kelvin. So these tanks we're looking at, have to be, there's a lot of pressure and energy going into this. And then once it's liquefied, it's at 20 Kelvin, have to be extraordinarily well insulated. But this is more or less rocket fuel. There's liquid hydrogen is used as a propellant. So it's not a completely new technology. It's just a matter of economic will to make it happen. Liquid gas tankers, storage, distribution, etc. Now you run your planes, you run your buses, and you run your grid off of it through the fuel cells, and then there's some, the heat can go to households for waste. So that's, pretty, and again, all of it turns to heat. The difference between a hydrogen economy and a carbon economy is that, while H2O is a greenhouse gas, it does trap heat, it goes away. And I can't believe it, but I just last, in the last class, I came across the number that I hadn't seen in a while, but apparently nature can sequester 4 gigatons of CO2 per year.
All by itself.
Yeah, so that's what photosynthesis is sequestering. We're making, we just did the math too, it's funny how it worked out, we're making approximately 40 gigatons. It looks like, yes, we're making about 9 to 10 times what nature can absorb. So it's getting stanky up in here. Yeah. Anyway, it's time. It's well past time, and I really hope these Paris talks come out well, and that our future starts to look like this. We have this technology here. Unfortunately, when the new Missoula College went in, we had to dismantle our hydrogen station, but we still have it, and it'd be great to get it running again. Okay, next figure is 10.9. Yeah, we really skipped forward. There's not a whole lot of figures here. I'm on 508, and this is the UK energy supply mix. 1960 through 2010, they've gone through a lot of their coal. Natural gas has come online. Their energy demand has stayed relatively flat, as has their population, and I can only assume that they've become more efficient with their insulation. And then there's a couple different terms. One's the alpha and one's the gamma. Alpha involves nuclear and gamma does not. let's just keep on rolling here. Actually, no, let's take a break. Like we said, 30 minutes, yeah.